In this lesson, we're going to introduce this idea of chemical formulas and chemical compounds and how we discuss them and represent them. Here's a quick overview, just kind of giving you an idea of what this lesson is going to be about. To start off with, we're going to talk about something called chemical nomenclature. Now, nomenclature is hopefully a word you've heard before. But basically, to kind of get us rolling, it's all about naming. All right, so chemical naming really is the key to this. So a compound, as you know, is a substance with a constant defined composition. We know that it's made of multiple elements. And of course, it's kind of important to recognize that we have a lot of compounds that are recognized. We recognize as humanity, we know a lot of compounds that are there. So the problem is then how do we exactly identify them and name them, because they're all important in some way, shape, or form. But of course, for example, we have down here water, that can be also known as dihydrogen monoxide. Table salt is also known as sodium chloride. Baking soda, sodium bicarbonate, muriatic acid, if any of you use that to help you balance out the acidity of your swimming pools. That's also known as hydrochloric acid. So what exactly distinguishes between them is that one of them is sort of a more common name, whereas the other one is part of a systematic name. And the systematic name is our focus here. So the systematic method of identifying our compounds is called chemical nomenclature. All right, so let's break down the chemical formulas. Again, this is mostly review here. But chemical formulas, of course, are these formulas that represent the number of the elements, atoms that are used to make a certain compound. So in this case, right, the chemical formula for a molecular compound right here is C8H18, right? You can see that it tells you there's exactly 8 carbon atoms and 18 hydrogen atoms together that form one compound, or excuse me, that form one molecule of the compound octane, right? This random compound octane. But again, the distinguishing nature of this compound relates this, right? So we have our chemical formula instead of ionic compounds. So the formula unit, again, is that basic fundamental unit, right? Not the molecule, but instead now the formula unit. And the formula, again, that you see, the chemical formula you see is usually written like this. Again, just like the other thing, we see some Al, some subscripts, some S's and O's, some elements, and some subscripts. But this one, again, is actually about the simplest repeating unit. So as we discussed before, right, with the covalent or ionic compounds, right, the formula unit is that single repeated unit. So let me go and use the color here. A single repeated unit that we see over and over again. That is not the red that I asked for. But do note, again, this is kind of like a simple one. So there are ones that are a lot more complicated. And whatever the case, they all have to be represented with the fundamental repeating unit, which in this case would be NaCl for the one that's in purple and green here, or in this case, the Al2SO43. And we'll talk about some more of what that looks like later on. So let's go and take a look at these. I want you to go ahead and kind of try these out on your own. I do want you to answer these, and we'll check out the answers later on. This is partly a review and also kind of tests a little bit about what you know about these compounds and formulas and how they're represented. So again, make sure you answer these, to give it a pause, and go and work these out right now. All right. Let's talk about our first major category of compounds that we want to discuss. And this will be ionic compounds. So let's talk about ionic compound nomenclature to start. Let's define what monatomic ions are. Monatomic. These are ions, as you can imagine with the word ions. These are ions that are composed of a single atom. That should make sense because mon, in this case, really is short for mono, right? Mono meaning one, and then atomic referring to atom. So single atom ions, monatomic ions. So atoms will gain or lose electrons, specifically valence electrons, in a very predictable pattern to achieve stability. So we've talked about this before. A lot of atoms become ions because it's more stable for them to be an ion rather than as a pure or solo single neutral atom. And of course, we have to satisfy the octet rule. And this is mostly for our main group elements, which are S and P block elements. So again, if you're not really sure what those are, again, going back here, so you have the S block over here on the left, you have your P block elements over here on the right. And so we're mostly talking about those kind of elements where we can predict very easily how they are going to lose or gain electrons. Metal atoms typically lose electrons to become metal ions. Non-metal atoms typically gain electrons to become non-metal ions. And of course, when they become, when they have, gained or lost electrons, right? So you lose electrons, what happens to the charge to become an ion? That's going to become a positive ion. And of course, I learned that before, right? That's going to be a cation. So that's your positive ion. And then these nonmetals that gain electrons, right? Electrons are negative. So when they gain extra negative, they become negative ions. And we know those as anions. Just to note, all those elements we didn't talk about, so the D block and the F block elements, those transition metals, those have a pattern that's a little bit less predictable, and we're not really going to get into that. But focus again primarily on those S and P block elements. A really quick review, we have this calcium atom. There's 20 protons and 20 electrons, but the important thing is that we have 2 valence electrons, right? So these 2 outermost electrons. So then, when calcium atom becomes a calcium ion, it loses those 2 electrons. You can see that these 2 that were there before are no longer there. And so as a result, it becomes a positive 2. And we do that, and we know we lose those 2 because it then forms another octet with the or the lower ring right there of electrons. It has 2, 4, 6, 8. It has those 8 electrons, so that's its octet. Therefore, the octet rule is satisfied for the calcium ion. Right, so to do so, again, it loses 2 electrons, and knowing that it's going to have this ring right here, that's now the new outermost electrons, and that's 8, so that's stable. Fluorine atom, right, as an example here, fluorine, right? Fluorine has 9 protons, 9 electrons, and this 1 electron right here, right? That's the 7th electron that isn't paired up. Well, as it becomes an ion, it's going to become stable by then pairing it up there. So a new electron has been introduced, and that as a result makes this fluoride ion more stable, and it now has the octet rule satisfied with 8 electrons in its outermost ring. So the method by which these 2 again become stable is a little bit different, but they achieve the same goal by satisfying the octet rule to become stable. The actual process by which that occurs has very specific terms, which are reduction and oxidation. So the term reduction refers specifically to the process of gaining electrons. It's kind of bizarre because the word reduction sounds like we're losing something, and yet we're talking about gaining physical objects. So in a way, we're actually not necessarily talking about necessarily the gaining of electrons to refer to the reduction process. It really is more about a charge, right? Because gaining electrons, that means you're gaining negative stuff. So we're basically reducing the charge, going from a positive to a more negative side, right? So as you reduce something. These form anions, right? Because you've gained electrons, you've gained negative charge, so these are negatively charged. And these are very commonly experienced by your nonmetals, right? So again, those are worth keeping in mind. Nonmetals, those undergo reduction to become anions. Oxidation, on the other hand, this is the process of losing electrons. So again, this is the opposite process of reduction. So something that, again, gains electrons, that's reduction, but the opposite process of losing electrons is called oxidation. These form positive cations because you're losing negative ions, so it becomes positively charged cations. And this is mostly experienced by our metals. A couple of memory techniques, oil rig. All right, you see this little guy right here, that's oil rig. OIL, referring to oxidation is losing. So that's oxidation is losing electrons. And then rig, RIG, R represents reduction, I is G, gaining. Reduction is gaining, and then even though it's not specifically stated, the word electron is assumed here. So oil rig, oxidation is losing electrons. Reduction is gaining electrons. That's how you can distinguish between the 2. You can also use Leo-Ger, or Leo-Ger. So Leo, oftentimes associated with the animal, the lion. So Leo the lion goes Ger, right? So Leo, losing electrons, is oxidation. Leo. Ger, G-E-R, gaining electrons is reduction. Right, so gaining electrons, reduction. So either method's fine, and that will be any method, again, that you can help memorize and know which process it is. That's also going to be useful. Let's go and walk through this process. So for each element that I've given you here, so 1 through 4, I want you to identify each of the following. 1, identify the type of element. Is it a metal or not metal? The type of ion it will form. Will it become a cation? Will it become an anion? Right, so we're assuming these are atoms first and then becomes an ion. The process that it undergoes, and then tell me the charge that will result. So let's work this out. The first one, oxygen. The first element is oxygen. So this is going to be, again, a metal or non-metal question. So looking back over here, oxygen is right there. Oxygen is a non-metal because it's towards the right. So it's a non-metal. The type of ion it will form, well, mostly we saw this from before. If you look back up here, non-metals are typically going to become anions. So this becomes an anion. Therefore, we got to know what process that it undergoes to become an ion. So is it reduction or is it oxidation? Well, again, we talked about this a second ago. This would be a result of reduction, right? Because you gain electrons to become a negative anion. And then what charge will you have? So this is going to be a little bit trickier. Well, how do we know, again, what it becomes? Well, let's go back to, again, how we know how many are gained or lost. So if you look back at these examples, right, we talked about the number of valence electrons that are going to be lost, electrons that are going to be gained. Depends on how many are already there. So we got to figure out how many valence electrons oxygen has. So going back to the chart, the periodic table, all right, oxygen, looking at this right here. Some of you have the markings up there to tell you that this is element, and this element is in group 6A. So that's VIA. So that means it has 6 valence electrons. So if you have 6 valence electrons, how many electrons do you think it will gain to become an anion? Well, it ends up gaining 2 electrons. So as it gains 2 electrons, it becomes a -2 charge. All right, go and try the rest of these out with sodium, phosphorus, and barium. So same process, looking at some of the logic we just talked about there, knowing where we get that information from. This is also worth memorizing here, if you can't tell. So each of these groups, the elements that are in those groups, typically have a known predicted charge. And so group 1, typically they become a group +1 charge. Group 2 becomes +2, so on and so forth. And we'll skip a few groups here and you kind of notice how we sort of range like this. The group 15 nonmetals become -3, so on and so forth. So go and commit those to memory. We'll talk about this more in the next class. All right, quick note on charge notation. Remember that the charges are superscripts, right? There's superscripts at the top right. And then if the charge is -1 or +1, you can omit the 1. You don't have to if you don't want to, but you probably should for the sake of doing it. Again, the mostly that we see. Sometimes though, with the computer formatting, sometimes a negative sign is hard to see, so sometimes I include a 1 anyway, but for when you write it out, you should only include a positive or negative sign. And you're also welcome to write the charge before or after the number. The choice is yours. So again, 2- or -2, they mean the same thing. Let's talk about how we name these. So the monatomic ions themselves, if you have just a regular old monatomic ion, when it comes to the metals or the cations, it doesn't really matter. No, excuse me, let me rephrase. It doesn't actually change. So whatever element you have that becomes a positive ion, we just call it that element with the word ion attached to it. So the name is unchanged. Therefore, K plus as an example, this would just be called potassium ion, right? Because K plus is positive, so we know it's a cation. So we just call it potassium ion. When it comes to metals, non-metals anyway, that changes a little bit. The last syllable we typically change to an IDE, I-D-E ending. And that I-D-E ending is vital. So this is not something that you should kind of casually be like, okay, IDE, whatever. I want you to recognize that this ending is important to the identity. So for example, you see S with a -2 charge. We just call it the sulfide ion. Notice how we don't really care about the fact that it has a 2 negative there. It's just the fact that it's negative, and we know that it's sulfide ion. We'll talk more about that relationship later on. But again, because sulfur is the element, but then it becomes an ion, so we call it a sulfide ion. And the chlorine, right, so right here, Cl becomes a negatively charged ion, therefore we call it a chloride ion. So this is true for these monatomic ions. If you have a single element, that's a negative anion, we change it to an IDE. Or if it's a metal cation, right, going from a metal, neutral metal into a charged one, we just simply add the word ion to the end of it. So let's talk about how we get into some of this nomenclature as a compound overall. Binary ionic naming rules really comes down to first identifying the type of compound that we have. And this is where I want to start off with this practice. It does say ionic compounds are composed of cations and anions, right? So ionic compounds, there's always that relationship between positive and negative. And specifically in this discussion, we want to talk about the word binary ionic compounds, right? A lot of times I'll abbreviate that BI, right? So for binary ionic. These binary ionic compounds are ionic compounds, right? Having positives and negatives, composed of only 2 elements, right? Just 2 elements, nothing else. So as you can imagine, if we've talked about these positive negative elements that are supposed to be added together, typically we relate these as both metals, combining a metal and a non-metal. All right, so just a single metal and a single non-metal combined in some specific way. That's a binary ionic compound. So the word binary, just in case you're not clear about this, this refers to 2, right? Let me do it over here. Binary refers to 2, but specifically 2 elements, right? Not 2 atoms, not 2 ions, but specifically 2 different elements. So that's what binary refers to in all these discussions. The name is written as cation first, anion second. Right? There's no additional sort of changes to it. There's no parentheses. There's no anything else. There's also an "-ide" ending for the anion. So this "-ide" ending gets attached to this element there. And there are no prefixes. So you may have heard of like dis and tris and tetra prefixes, mono prefixes. They're never included here. The formula, on the other hand, does have a little bit of work you need to do. First of all, you have to recognize that the total charge has to be 0. So this x, then the number, y, and the number, right? X is your cation, y is your anion, and it has some subscript number to the right of it. That tells you again how many there are of each ion. And the total charge overall has to be 0, right? Meaning there's going to be some positive charge here, there's going to be some negative charge here, but it's never represented. The charges of the individual ions are still present, but it's understood and never explicitly written out as a compound. So let's go and take a look at some examples. First of all, going from a formula to a name. All right, let's do the left side first. So going from a formula to a name, you have Na2O. All right, first of all, we have to identify the type of compound it is. It's an ionic compound. I know that because this is Na, the metal. This is oxygen, a nonmetal. So this is an ionic compound. But more specifically, it's a binary ionic compound because there's only two elements. As a result, we name it like we saw before. Going from a formula to a name, I have a bunch of letters and numbers. Give me a name, meaning I'm going to write out its name. So the first one, Na, right? This is your positive cation that gets listed first. That becomes sodium. And then O, which is our second element, that's the negative ion, is the anion. That becomes oxygen, except remember the second word, the second cation, the second anion, that one gets listed as an ide ending. So this becomes sodium oxide. Kind of be careful about that because some of us might have been trying to do like oxygenide or oxyide or something like that, oxygide. But this one just becomes oxide. And you probably heard of that phrasing before. What about MgBr2? All right, same thing. So MgBr2, we know that this is a metal. This is a non-metal, right? Magnesium and bromine. Got to look at those identities on the periodic table to know it's going to be an ionic compound. But more specifically, it's a binary ionic compound because there's only two elements involved. So Mg is magnesium, right? No change to the positive cation. And the second element, this becomes bromide. Notice, all right, as I stated before, that neither of these names have any kind of prefixes with it, right? There's no additional like di or tri, even though the formulas might have represented that, right? So the two there, neither of those are shown in the names of these compounds. Also note, again, that the ide was added for both of these, right? The IDE is very characteristic of these monatomic ions. So bromine is just a single atom that has a -1 charge, so it becomes bromide. Right, on the right side, this one takes a little bit more work, going from a name to a formula. Lithium nitride. So again, what kind of compound is this? Yes, it's a binary ionic compound. We know that, but let's make sure we know why. Lithium is one metal, right? Is one element. Nitride comes from a non-metal, right? Nitrogen. So knowing that has an IDE ending tells me it's just the single element nitrogen, just one nitrogen, right? There's no additional things to it. So in this case, right, we know it's binary ionic. So therefore, we follow the binary ionic rules. So in terms of how we do this, right, we've got to combine lithium and nitride. Well, what are their charges? Well, lithium, right, because the group 1 element, this becomes a +1 charge. This is from that little chart that I asked you to memorize earlier. What about nitride? Well, nitride, right, that's going to be an element N because it's nitrogen, and it's the ion form of it. So that actually ends up being -3. So again, that comes from that chart, knowing that elements in that group are always going to become an ion of -3. So how to combine these two in a way that ends up canceling out so they become overall neutral? Again, if you're not sure what I mean, let's back up here. The total charge has to be 0, right? So we have to add enough, we have to eat by these subscripts so they're overall neutral. Well, if you have a -3 here and a +1 here, right now if you combine the two, that wouldn't really give you a charge of 0, right? Because the -3 is greater in amount than the +1 here. So how do I make this so that they overall, again, cancels so that it becomes neutral? Well, what do I have to do with my lithiums? Well, I probably want to include a couple more lithiums, right? So Li plus here, include another lithium there. So overall, that's 3 positives to counteract the 1 -3 over here. So altogether, this becomes Li3N. We have a single nitrogen ion, has a charge of -3, so we don't include a subscript there, but we have to have 3 lithiums that are each +1, but there's 3 of them, so there's 3 there, and then we write Li3N. Right, so assume that the +1 charge is included with the lithium, and then -3 is included with the nitride. Barium fluoride, same way. All right, this time we have a couple of information we got to look at. Again, this is binary ionic because you have a metal and a non-metal. Right, it has the IDE ending as well. It's binary ionic. So let's put this together. Some of you might find what I just did there a little bit long and tedious. So let me give you a bit of a shortcut there. Barium is a is a +2 charge. Right, you got to go find that on the periodic table. Find that it's in that column that all the ions are +2s. Fluoride is a -1 ion, right? And so now we got to combine these two so that it overall is a neutral charge. So kind of a way to help, that I keep track of this is that underneath that I write the individual charges. So down here are individual charges. Right, so that's what the -1 and the +2 represent here. And then on top, I write this total charge that I have working with. Total charge. So what that means is that my total charges for the positive and negative have to be the same. Well, one way to do that is kind of look at this as a least common multiple. Now, hopefully you remember what least common multiple means, which is basically what number can both of these numbers, 2 and 1, what can they both divide into equally? With no remainders and nothing left over, right? So it turns out that it should probably be a +2 and a -2, right? That's the least common multiple between 2 and 1. So what do I do to make that happen? Well, to make that happen, barium, I get multiply that by 1. To go from -1 to -2, right? To get that least common multiple, I multiply this by 2, meaning I double the fluoride ions and I keep the barium ion simple as 1. So to write it out, barium, right, that's a subscript of 1, which I don't ever include. And then fluoride, F, right, I have to have 2 of them to match the charges over here. So I write BaF2. So that's my answer for that one. All right, so there are some other example and practice problems here. You are welcome to try these out. I encourage you to do give these an attempt. And notice that a lot of these, again, are about a lot of different combinations of different elements and writing them out as ionic compounds. But we'll definitely cover these more in detail in class, so make sure you give those a shot. There's also a common errors one, which you're welcome to attempt. But again, all of this is something that we can discuss later. But please do attempt the ones that I have asked you to. All right, that'll do it.